Today's lecture is actually, I think, one of the most important and one of the most interesting having to do with simulation. So far, what we've done in this class is to simulate probabilities for different kinds of models, particularly probit and mixed logit, but then you can generalize those concepts to any kind of model, essentially. But so far, when we've done that, we've simply stuck them into a maximum likelihood estimator and estimated on the basis as if they were true probabilities instead of simulated probabilities. We've just done that mechanically without really questioning whether that's an appropriate approach. In today's lecture, what we're going to describe is how do you use these simulated probabilities to do estimation. And there's several approaches that we're going to discuss. One is maximum simulated likelihood. That's what we've done so far. You just pretend it's the true probability and stick it in. What we need to know there is how does this affect the properties of the estimator? And we'll find that it actually does affect the properties, and it's only under certain conditions that these estimators end up having desirable properties. So the procedure we've been doing so far, we want to formally derive what the actual properties of that are. Is it consistent? Under what conditions is it consistent? And what's the variance? We'll see that there's actually the criteria that are needed for consistency here and for efficiency are relatively stringent. And what that has led to is two other forms of estimation that obtain consistency and efficiency at, well, at least consistency and maybe even efficiency with less stringent requirements, more obtainable requirements in your simulation. And however, we'll see that that advantage comes at a cost. And we want to identify what exactly that cost is. So there's three different types of simulation estimation procedures that we're going to discuss. Maximum simulated likelihood, which is what we've done so far. Maximum method of simulated moments, and method of simulated scores. These two are an attempt to deal with some of the issues that arise with maximum simulated likelihood. I want to go through this intuitively first. I think the results make intuitive sense, and I'd like to describe what those are. And then give a formal proof of the properties of all of these estimators. To do that proof, I want to do some background, which covers material you should have done in 240A, but I want to redo it in a way that makes sure we're all on the same footing, and secondly, leads well into what we're going to do. And then show what the formal, what the distribution of these three estimators are. Okay, so for each of these estimators, there is a non-simulation analog to it, and the simulation just adds a new wrinkle to the old estimator. So what we've had so far, what you've done in your standard econometric classes in the past, is maximum likelihood estimation. This is defined, the maximum likelihood estimator can be defined in either of two ways. It's either the argument that maximizes the likelihood function, which we can write as, for parameters theta, the probability for observation n. We've got capital N observations, and this is the average log likelihood. Today, for these kinds of proofs, you'll see that taking averages of everything makes life easier for doing the proofs. Obviously, maximizing the average log likelihood is the same as maximizing the likelihood itself, but the proofs work out better when we divide by sample size, or it's just easier to see the proofs. So this is one way of representing it. The other way is to recognize that this maximum occurs where the gradient is 0. And so you could define this equivalently as the parameter that such that the average gradient is equal to 0, where for maximum likelihood this gradient is equal to the derivative of the log of the probability. Okay. So you can also define maximum likelihood as being the value of the parameters that solve this equation, or another way to look at it more succinctly is the root of this equation. Maximum simulated likelihood is simply the analog to this that replaces the probability with the simulated probability. So maximum simulated likelihood, I'm using with two hats, is the argmax of where this upside down hat is a simulated value, or equivalently one over n, where we have simulated derivatives, gradients, where those simulated gradients, this is important, they don't have to be, as we'll see later. But for maximum simulated likelihood, the simulated gradients are equal to the derivative of the log of the simulated probabilities. So you just have that. What are the properties of this? Generally, we will have an unbiased simulator for the probability. All the simulators we've looked at so far are unbiased probability simulators. What that means is that the expectation over the draws, so this is the expectation over the process by which you take draws of the simulated probability, is equal to the actual probability. So we have an unbiased simulation process for the probability itself. However, when we put that into maximum likelihood, we're taking the log, and that nonlinear log transformation does not pass unbiasedness through it. Essentially, the simulation of the log of the probability is not unbiased. That is, the expectation over your random simulation process of this does not equal the log of the probability. So what we've got is our simulation creates